So, thank you guys. So let's get started with step-by-step Kubernetes observability with eBPF. Oh, I switched too fast. So maybe before going there, I'd just like to say how much I like Porto. I was here the second time, presenting just the first time, but I really like the landscape. You can just sit anywhere, observe it for hours, and really like it. Another thing that I like to observe is Kubernetes services, and that's what we are going to talk today. So I'm Rinor Maloku. That was an introduction for me. I co-authored the book Istio in Action together with Christian Posta. And what we do at Solo is we provide the platform for all application networking concerns. It covers stuff like Istio, Envoy, Cilium, and then this is running natively in Kubernetes. Our stack is covering the network's layers from layer 3 up to layer 7, and then we go beyond and cover, for example, GraphQL, and we added this straight into the Envoy proxy. So we have a lot of experience within the networking layers. What we will cover today is only the layer 3 networking, where we have less information. We have information such as the IP address. When we start the TCP connection, there is the source and the destination. So we get the IP address of the source and the destination. With that, we already can gain some benefit. By knowing the source IP address and the destination, we can understand which services are talking or communicating with each other in a Kubernetes cluster. And for that, we are going to use eBPF today. So today, we will have a short, brief introduction to eBPF, how to develop for eBPF, and then we will demo this in an environment. So what is observability? Observability, there are multiple ways of explaining it, but the most simplest way is that it is the ability of a system to be understood by checking its external signals, like metrics, traces, and logs. So within observability, there are a lot of stuff. We will cover just a small portion of understanding which services are communicating with each other. And you would like to know those inter-service connections quite often because that allows you to reduce the amount of access. If you know which services are communicating, you can add specific policies that allow service A to talk to service B, but not to other services. This enables you to implement privileges, like principles, like the principle of the least privilege, so that only one service can communicate to the others and not vice versa. Such, you can increase security. Another way of implementing the same that we will show in the demo is just using a service mesh, which adds a sidecar when a client is talking to a server, and then the sidecar will generate metrics, traces, and logs, and you will get observability. But usually, you gain way more benefits when you use a service mesh, but that has as well the trade-off that it consumes more resources, and if you don't use all those capabilities, a simpler solution is welcome. So what is BPF? BPF stands for Berkeley Packet Filter, and this obscure technology had the goal to improve the tools for debugging the network traffic, like, for example, TCP dump. It allows you to extract information from the kernel and show those to the user in the user space, where you run TCP dump. Alexei Starovoitov had the idea of, if we can extract information from the kernel, why not make it in such a way that we can add logic and get output, and this for every system call, not just for the networking calls. And that is what eBPF stands for. It's Extended Berkeley Packet Filter. So why would we use eBPF? There are a lot of uses. One of those is observability, because you can listen to every request that's happening, or every system call that's happening in the kernel, and you can understand which processes are opening files, reading those, modifying those, or what connections are occurring, and so on. Another one is networking, because BPF was initially built for networking. That's the layer that it helps the most. You can see where a traffic is starting, where it's ending, how much traffic is going back and forth, and so on. And then finally, we have security, because we hear every call. We get every call, we can add logic and stop some calls. We can create allow lists and deny lists to deny traffic to some destinations. And this is the example that we are going to cover. So to build eBPF programs, we already have some solutions, but all of those solutions contain the user program and the kernel program. The user program is where you write what the end user will see. Like, for example, in TCP dump, the end user sees all the output of the traffic that's going back and forth. Then it generates the BPF bytecode and loads it into BPF within the kernel. Initially, it's verified to make sure that it doesn't cause some issues within the kernel by blocking the traffic and so on. And then finally, it either writes into a data structure or it sends the output directly to the user program. The user program can show this traffic or as well just query and read the data that was stored in the map. So every eBPF program has these two parts, the user program and the program which is added to the kernel. One way to build such a program is using the BPF compiler collection, and it's called a collection because it already comes out with a lot of tools. Here is the entire list, or actually not the entire, because even more new ones are added. We will show an example of building a TCP connection listener with BPF, with a BPF compiler collection. Initially, we will just skip. So it is as well composed of the user space program, which is written in Python, and the kernel space program, which is written in C. It has to be compiled at runtime. That's why it has some overhead in the beginning. But it has a good benefit that it has really good documentation, and I really like good documentation. So that's one of the big pluses for using BCC. The other solution is libbpf and BPF core. Here, you can compile it once and run it everywhere, so it removes this overhead initially. And with libbpf, you write both the kernel and the user space code in C, so you don't have two programming languages. That's another benefit, but its documentation is way worse. And finally, we had this question, like, what if we could only write the kernel program, not the user space program? Quite often, the information that you want to print can be simple text, so we would benefit a lot if you can write just the kernel program, and that's where we built Bumblebee. Bumblebee is a small binary that allows you to write only the kernel code and build it as a OCI image, meaning that you can publish it in Docker Hub, share it with everybody else, and build tools which are making use of eBPF. As well, you can run it, and another benefit is that you expose this information as Prometheus metrics, so you can easily integrate it with your observability platform. So with that, we go to the demo. You can as well go through the demo by using this link, which is bit.ly eBPF observability. The demo will take like most of the time that we have left. So let's switch to the demo, and we get started. We have some information here. Like, can everybody see the text? Should I zoom in? Like the last guy, can you see the text? Okay, I got so, okay, so that's good. So let's skip from eBPF. That's some explanation, but it's kind of the same that we covered. And let's go to our first program, which is this BCC TCP Connect. We will go to the files and just check out this file. Here we see the code. We said that the program is composed of the user space program, and this is the kernel space program, where we create a K-probe on the TCP v4 connect. This means that whenever a TCP connection is being created, we hook and add extra logic. The extra logic is quite simple. We are just sending back the source address, the destination address, and then the port. But we use just the source address and the destination address. We are using this text and creating a BPF program, and then this will load it into the kernel, and we get a handle on it with a variable b. If we check below, we are starting the program and creating an infinite loop where we read from the source address, the destination address, and we print those. So let's initially make sure that this is working. So we run Python 3, BCC, TCP Connect. So we are using the first solution, which is using the BPF compiler collection, and now we are taking information from the kernel and printing those out. This is just the connection with instruct that's keeping the platform alive. Let's run another curl command. So we send a request to example.org, and here we see that we got the example.org IP. So we are injecting some custom logic into the kernel, which is just extracting the source address and the destination address for every TCP connection and printing it out. And then we pick this print information into the user space program and we show it here. So the code here could look like a very complex code, but actually, let's say when we are printing this, how do we get the information? We see that we get the task, process ID, CPU, and so on by using the trace fields. So we can just go to Google, search this one, and add something like BCC. And we get the reference guide, which explains what this does. Let's zoom in a little. And here is the explanation that this is just reading from the output that we do in a step within the kernel program, which is the eBPF trace print K. And we have this one documented as well. So here. That means that whatever you want to build, you will just go through the reference guide, understand how to get what you want, and then just apply it. The next part is using eBPF. So eBPF, you write both the kernel program and as well the user program with C, and you can compile it so that when you move it from one platform to another, you don't really need to recompile it or compile it at runtime. So let's go to here. We will skip this part and go directly to eBPF. We will move to the eBPF tools directory. So one thing that you need to do, and we did it ahead of time, you need to go and download this repository. So and we did this ahead of its time, so we have it locally. And it has some explanation, so you might want to check it out. And here we can copy our code for this TCP Connect application built with eBPF. So this is the BPF, so the kernel code. And here, if you go to the bottom, we see that we add the hooks to the kernel. We do this when we start the TCP v4 connection and when we close the TCP v4 connection. And then we add the logic, which is the same, just extracting the source address and the destination address. We add the capability to count how many times this connection was started. So let's copy all of these files. And then we can make this binary. Paste here. It will take some time initially because it's being compiled, but then it will be much faster to be started. TCP connect. So let's switch and execute the curl command. And here we see the request to example.org, and as well the connections that are being kept to keep the platform alive. So this is with eBPF. Now we built a binary, and you can share it into all Linux systems. So the question that we had is like, if we want just to get this text outside, like, can we just write the kernel space program and skip the user program? And that's what we do with Bumblebee. So let's skip to the next part, which is Bumblebee. I know this is a little too fast, but I want to get to the demo, which is the most interesting part of this. If you are interested more into eBPF, we do some extra workshops into how to write a BPF program that we go into more detail into the code. Bumblebee is a binary that you can run and install locally. You execute it just by typing B, and you have to add it into the path. So let's print the version. So we have it ready. The nice thing about Bumblebee is that underneath, it still is using eBPF. So all of those binaries created with eBPF can be made use of, and you need to make small changes into your application. You only need to specify, like, how do you want to output the data. If you start a new program, you can execute B init. You select the language. We are supporting only C, but we plan to support Rust if we have customers asking for it. Then you can select, do you want to listen for network connections or file system, and then you select one of those. what data structure you want to use. Do you want to use a hash map or a ring buffer? Let's select, for example, hash map. Now, do you want to print simple text? Do you want to have some counter or gauge? Let's go with print. You name the program, probe.c, and this writes a file. It prepares a file for you, and it gives you some information on what you need to change. You can change the license if necessary. You have to add the dimensions, so what you want to print, and then the data structure, and here is the connection, so basically the hook, and you have to change the logic on how you want to return the data. Do you want to store it into a map, and so on. In our case, we will just use the same code that we had for TCP Connect. So let's go to that part here. So this shows what is the difference. So basically the difference is we are just specifying that we want to have a counter. So we used the same eBPF code, but we updated it just to specify a counter. So this is the change that we made. And this is all we need. The next part is we can just copy it locally. Let's copy it to this location, paste. And then we can build this as a container image. So let's paste here. So now we are building this as a container image, which is called localhost and so on. I have a Docker registry running locally, so I can push to that registry, but you could use anything. You could use Docker Hub, GCR, and so on. This usually is quite fast, not more than 20 seconds, and then we can go to the next part. We can run this. So now I am running the BPF program, and this is the user space part, which is only getting this information. We use the same logic as earlier. Here is the destination address, the source address, and how many times this connection was started, and the same for this one. If we make a curl request, we see again that if you go back, we see that now we got one connection to this external address. So now we are gradually counting all of the requests that are being started. So this is good, but another thing which is really powerful, and what we will use next, is that these information are exported as well as Prometheus metrics. Let's grab for source address. Maybe let's make the curl command as well silent. So here we have all the metrics for the connections that we got to a source address from a destination address. So these can be fed into or pulled by Prometheus, and then you can use this information. So what we will do next is we will run this application that we built within a Kubernetes. I think I missed a step. So let's check this one. Let's stop this application. And as well with Bumblebee, you have the option of pushing this to a registry. I will paste this. So with a bpush command, we push this to the local registry, which is localhost 5000. So what is the benefit that when we make BPF programs shareable? Now, anybody in the world can use this. No matter how simplistic, you already can gain benefits. And this is what we will see. We will run the book info application, which comes from the Istio community. So now all of these are running. We can get the pods, and we will see that the containers are being created. Let's go to the next step, which is deploy Prometheus, because we want to pull those metrics from eBPF from the TCP Connect tool. So let's create a namespace, paste it here. And then we use Helm to deploy the Prometheus deployment. Now we want to deploy the TCP connection that we built with Bumblebee. So we have to wait until the Prometheus deployment, or we can switch to the second terminal, paste it here. So this is the TCP Connect tool that we built, and it was pushed to the local registry, and now I'm pulling from it. After, when we use a daemon set, we make sure that one pod is running on every node, so we can see all the connections that occur on every node. So just to verify that, let's get the pods. And here we see that we have 3 pods for Bumblebee, which is the same number of nodes. Okay, get the nodes. So we have one of this TCP connection instance running on every node. So with this, we can go to the next step, which is add a pod monitor. A pod monitor configures Prometheus how to pull metrics, and we are configuring it to use the endpoint, the port HTTP monitoring. If we check it, it's the port which is exporting the metrics. So let's apply this one. And with that done, we can generate some traffic. So now requests will go to the product page application, which is a service of the book info solution. It will start a connection to the other services. And no matter in which nodes these are, we have a TCP connect binary running on every node using the daemon set. So we see all the connections, like where do they start, where do they end, and we expose this information, which is pulled by Prometheus. Now we only have to visualize this. So to visualize this, we built a sample application. Let's add the cluster role binding, because we want to correlate this information with Kubernetes information. And then we run the solution, so which is the eBPF program. So now, if we just start traffic again, or it already has the traffic, let's run it once more. So we have it here in the history. Or let's scroll up a little, and we have the method. So we just generate some more traffic, and we can switch to the application, and we already see all the connections that we have. Let's move this to the side. So the first request is going to the product page application. The product page application wants to pull some more information, like the reviews for the product. And then the reviews product will pull more information from an additional service, which is the rating service. And we got all of this information by just correlating the metrics that are pushed to Prometheus, and then pulling information from Kubernetes to see all the IPs and the names of the pods, and then combining those together. In such a way, you only have a small binary running on every node, exposing metrics, and you can visualize all the service-to-service traffic using it. So this was how we can gain observability over our platform in a very lightweight manner by adding and making use of eBPF, which is injecting some logic in the kernel, exposing this information in two formats. The first format is basically just the textual format, and the second one is Prometheus. And then you can do anything with this information that you want. In our case, we just wanted to visualize this in your UI. So with that, we can go back to the presentation, which is like an access. So if you want to try it out, like build your own solutions and still have a hello world example to get you introduced to eBPF, the BCC, to libePF, and as well to Bumblebee, you can follow that guide. And for more, you can contact us at solo.io. We are, besides Bumblebee, we are covering a lot of the network stack layer, and a ton of it is quite interesting, as well as, or mainly Istio. So thank you for joining, and do you have any questions? And just simple ones.
Thank you very much. So you heard our speaker, just ask away. Simple ones. Nothing too hard.
Mainly.
Just raise your hand.
So I can ask an answer that I know I forgot to mention. Like, eBPF won't be something that every developer has to use. It's mainly the people who are building platforms or tools that will be used in the platform. Like, if you are building web applications, you don't really have to learn eBPF or something like that.
Does anyone have a question? Maybe another demo? I don't know. So, if no one has a question, we want to thank you, Rinor, for your awesome presentation.
It was a
Thank you
pleasure.
very much.
Thank you, guys.
We have
Thanks everybody.
Oh, sorry. We have a question there. Sorry.
I have one here. First, thanks for your talk. I just have a quick question. So if we have multiple microservices and you want to know their interactions, which is the best or the easiest way to get to know which service calls each one? So using an eBPF-based program or a project?
So if we have, I will restate the question just to make sure that I got it right. So if we have many services and we just want to understand the connections, what would be the way to get this information?
Yeah.
And you just want to know the service-to-service information, nothing else. Like in that case, yeah, you could just run something like eBPF, collect all the information, and that's it. And it doesn't have to be like a long-term solution. You can get that information with eBPF. If that's all you need, that's good. But if you want to make sure that the same connections are being done in the future as well, you can keep it running, and so on. But eBPF is a very good solution to understand the system, and that is one of the cases that you would use.
Okay, thank you.
Yeah. You're welcome.
No more questions? Okay, another round of applause, a double one.
Yeah, thanks, guys. Thank you.